Cool. Awesome. All right, so welcome back. Lecture 2 here, talking about cause and effect today. Before we get started, we will be doing a few announcements here. So everyone should be assigned to a lab by this point. If you have not been assigned to a lab, please reach out or post on Ed. Lab 1 is also done. Lab 2 will be released on Monday. Well, okay, sorry. My screen was like blank for a second. Yep, homework 1 will be released today. So first homework of the semester, it'll be due next Thursday, and you'll be able to turn these in. If you turn them in early by one day on Wednesday night, midnight California time, then you'll get 5 bonus points. And this is going to be kind of the rule in general for homework assignments. So if you're someone who likes to start early, definitely do that. This is an advantage to that. Office hours begin next week. So these will typically be noon to 8 p.m. from, I believe, Tuesdays to Thursdays. So look out for more information on that. You can check out the office hour times on the website once they get posted. And then the instructors will also post their office hours. We'll announce that by Monday next week. And we'll probably try to do them like outside of the Tuesday to Thursday window, so that if you can't make Tuesday, Thursday, at least you have some options on like Monday or Friday. So we'll try to keep it a little bit separate there to give you guys more options. Cool. Any questions? Is the homework hard? I mean, if you're coming to lecture and you're keeping up to date with the material, doing your labs and stuff like that, then it should be doable. Cool. And yeah, that's a good question too. So our bonus points awarded if the lab is turned in early. So we only give bonus points for homework and project. Can we get a link for the slides? The link for the slides should be on the website. So that website that I showed you guys is just data8.org/SP22. You'll have a schedule of every single lecture, and then there'll be a link to today's slides, today's demo, if we have one. Today, we actually don't have a Python demo. This is pretty much the only lecture where we don't have one. And then we also have the video, and that gets posted later in the day. Cool. All right. So let's get started with the actual lecture. This is pretty exciting. So today we're going to be talking about links and relationships, I guess. Not between people, but just between data. So not as emotional, I guess. But basically, we're going to talk about links here. And so we're going to be looking at this study as an example. So this was published in 2020. It's basically a report. And it says that regularly eating chocolate is linked to 8% lower heart attack risk, right? So that's kind of what we're going to be going off with. And so what does this exactly mean? When it says linked to 8% lower heart attack risk, like any thoughts? What do you guys think? Like when you see that, when it says it's linked to that, if you had to interpret that and maybe say that in English or something, how would you say that? Correlation, causation, association, associated with, should eat more chocolate. I like that. Relation, correlation. Yeah. So those are good answers. Correlation is probably a little bit more technical. We will talk about correlation later in the course. But yeah, found similarities. That's pretty good too, I think. Yeah, and you guys are kind of like pretty much in the right spot there. So what we're going to typically call this is observation when you have these things being associated. It's association. We're going to call this association when two things are linked. So that's what we're going to talk about. So there's like some sort of relationship, then we're going to call that an association. So that's going to be the terminology we're going to use in the class. All right, so try to remember the association. The data moves together. That's a really good way to explain association as well. So, if you look at people who eat more chocolate, their heart rate risk is like 8% lower. So they're moving together. Maybe they're moving in opposite directions. That's okay. But the point is they're moving together in general when you look at individuals. And so we're going to call that an association. And then there's also going to be some additional terminology that we're going to cover here. What is the association about? What is it talking about? How do you assess association? How do you even try to come to an answer on whether two things are associated? So typically in this class, we're going to be talking about observational data for the most part. And so that basically means that you're observing something that's already happened. So you're not having a direct influence on what could happen. You're just observing data as it already is. So that's typically what we mean when we say observation or like an observational study. And so the individuals are going to be the subject of the study. And so individuals could be actual humans. They could be entities like a business. They could be like animals. It could be anything. It's just like, what is the subject of your study? What is the thing that you're studying? So that's the individuals. And they'll typically be like participants in the study. And so for this particular article, or the individuals that were under observation, that were observed, was about 300,000 US, Swedish, and Australian adults. And this was across actually several studies. And then there's also going to be this concept of a treatment. And so treatment doesn't necessarily mean something that's medical. It just means that it's sort of some sort of like change or some difference that's going to be applied to some of these individuals. And so in this case, it's chocolate consumption is kind of the treatment. And so, you know, you might be asked to consume more chocolate, or maybe you did consume more chocolate, either way. But that's kind of like the treatment. So that's kind of the change that you're trying to look at. And then what is the result of that change? You're going to look at what the effect that might have on an outcome. And so the outcome in this case is heart disease, right? And so typically, this is going to be the general setup we're going to be seeing a lot throughout the course. And that's the basic idea is, you know, we're maybe assigning a treatment to some people, and then we're seeing what the effect there is on the outcome, if at all. So that's the basic idea. And so there's going to be two questions that we're going to try to answer from these studies. So the first question is related to relation. So basically, is there a relation between chocolate consumption and heart disease? And so again, here we're going to call this an association. And this basically just means like some sort of relation, any relation really, some sort of link. So this is a pretty soft statement. We're basically saying like, is there a relation between chocolate consumption and heart disease based on that report? And so I can just go back to that slide so you guys can see it again. So let's go back to the study. So basically the study found that people who ate more chocolate had 8% lower heart attack risk. So does that imply a relation, an association, in your opinion? Yeah, maybe, yes, yes. Most people are saying yes here. Yeah, so it actually does. It does apply an association, at least within this study, within the people who were studied here, right? It may not necessarily be true for the entire population of all adults in the world, right? I mean, this was just 300,000 adults in like 3 specific countries, right? And so within those people, the study did show that there's an association. So that's good. So it kind of does confirm that at least. But that's a pretty soft statement if you think about it. It's just saying that there's a relationship between them. But is it causal? Exactly. That's the question. And so that's kind of the second question is, you know, is it actually causal? Sorry, my slides are being a little weird. Okay. So another statement that you could make, which is a stronger statement, is that chocolate is not only associated with or linked to lower heart disease, it actually causes the heart disease to go down. So that's what these articles are saying. And it's interesting because these articles came out like just right around or right after the time that report came out. So some people wrote these, and basically they went as far as to say chocolate's actually good for the heart. Is chocolate heart healthy? Study says yes. So this is a much stronger statement. If you think about it, right? And so this is going like one step further, basically. And so the next question then is basically, does chocolate consumption lead to a reduction in heart disease? And this is a causal statement. So what do you guys think about that? Based on that same study, do you think we could conclude this? Not necessarily. Most people are saying no, but few folks are also saying like not enough information. Some people are saying the study was backed by chocolate companies. Yeah, so you know, in general, like just from that statement, just observing that simple number that like it went down by 8%, that alone isn't really telling enough. Like we don't really know how this study was constructed. We don't really know if it was like an observational study or did they like go to some people and say like, hey, you guys eat chocolate, you guys don't eat chocolate, let's see what happens, right? Like it's not clear yet. You could prove it. There is a way to prove causality, but you'd have to be really careful with how you design an experiment, how you actually collect this data. And so this concept of saying that something leads to something else, it's a stronger statement, it's causality. So that's the main thing to keep in mind. Association is like any sort of relationship. They kind of move together maybe, but causation is not only do they move together, but it's actually because of this thing that this thing is moving with it, right? So it's a stronger statement. So, causality always implies association, but it's not the other way around. Cool. And so in general, assessing causality, it's pretty hard to do. For this particular case, there were a few folks who like kind of dug in deep to the study and basically were a little bit skeptical of the findings. So it wasn't totally clear in this situation that causality was proved. So a few questions here. Can observational studies generate causation? So generally, observational studies aren't going to be enough to determine causation, actually. You have to do something a little bit more than just observe what happened. And we'll definitely talk about that in this lecture. That's a really good question. Cool. So let's look at another example. And this is going to be, we're going to start off with association, but we'll go to causation. So we're going to go back to London in the 1850s. So when you think of London in the 1850s, like what images come to mind? I mean, besides the one I'm showing you here, I guess. Gross, yeah, I guess. Diseases, rats, Charles Dickens, all fair. Cholera, yeah, a lot of you guys are going a little bit ahead here. Lord of the Rings, nice. Like, these are really good. Yeah, so cholera was pretty common at the time, was really kind of rampant. And in general, like, back then we just didn't have the same technology we had today. And so diseases just spread so much faster. We didn't have the same knowledge, same science. So, things just spread a lot quicker. And this is a cartoon from the times and from that time, and basically says a court for King Cholera. So basically, cholera is the king, and then everybody else is just kind of at cholera's mercy. So it was spreading super quickly, and it's no one really knew like what was happening. Like no one really knew how it was spreading. It's kind of similar to the early days of COVID, I guess. Like we didn't really know at the beginning like how it was spreading, but for this case, they like didn't know for a very long time. And there were a lot of hypotheses about how it was spreading, why it was spreading. And one really big one was miasma. So this one, somebody mentioned it. I don't know how. But basically, the idea is bad smell given off by like waste and rotting matter. So this was like one of the prevailing theories that like these things were like bad smells effectively was causing cholera, which like doesn't seem that unreasonable, I guess. And so this is believed to be the main source of cholera. And so there were some really prominent believers in this actually. So Florence Nightingale was one of them, Advent believer, and Florence went as far as to actually go and like clean a bunch of hospitals because to like remove all the bad smells. And even though that wasn't really what was causing disease, it probably was actually a good thing to clean the hospitals. So kind of worked out in some sense. And another prominent believer was Edwin Chadwick. And so Edwin also believed in this kind of hypothesis and basically went out and tried to advocate for cleaning the sewage system, which again was probably a good thing, not necessarily related to the disease, but still helpful. So kind of interesting to see that. And there are all kinds of interesting hypotheses around like what can cure it too, which is kind of funny. So like there are a lot of this concept came out about like just moving to clean air, and just moving to areas with like better air. The kind of nursery rhyme pocket full of posies was actually also came about during this time. So it was like literally just go grab a bunch of like little flowers that smell good and like you'll get better. I don't really get the firing off barrels of gunpowder part because I would imagine it doesn't smell that good, but I guess some people maybe like the smell or something. And then, yeah, there was even like a really funny one where people were just like, let's go get air from the top of the Eiffel Tower and like bring it down. And then that air will be better. And then they'll make us like get rid of the disease. So, lots of creative ideas. And we saw lots of similar ideas like this during the pandemic as well, surprisingly. So, injecting disinfectant or somehow getting the sunlight into our veins or hydrochloroquine or, so it's kind of the same thing. History kind of repeats itself in some ways. But yeah, people always come up with various ideas. So yeah, in any case, basically there's always suggested remedies for all these diseases. But it's always helpful to actually look into the data and see what's actually going on. Cool. So there's one person, John Snow, who didn't really agree or believe these hypotheses. He kind of observed something interesting, something different, and thought that maybe there's a different explanation and potentially different solution to the problem. So he noticed a couple things. The first thing that he noticed was that people in houses that live right next to each other weren't necessarily having the same outcomes. So you'd have like a house with, let's say, like 6 people in the family, and then everybody dies of cholera. And then right across the street, you have another family of like 5 or 6 people, roughly same income, roughly the same, average age in the family and all that stuff. And they were totally fine. So that was a little bit strange, especially if you're thinking that it's like bad smells, right? Like a bad smell should probably permeate to both sides of the street and go to both houses. So that was a little bit strange that houses that were technically like basically right next to each other had such different outcomes. And this was happening like really, really often. It wasn't just in isolated cases. And then also he saw that the symptoms were kind of interesting. The symptoms were like diarrhea or vomiting. So he felt like it might be something dietary related potentially. Again, still seemed a little bit weird because like, why would someone across the street from me have like such a different diet? But it seemed like something was pointing to that. And so he did what all kind of great data scientists do, which is he collected some data and then made some visualizations. So we're going to take a look at one of his visualizations. It's really cool, actually, really creative. And so what he did was, this is the Soho region of London. And so what he did is he went through all the neighborhoods and kind of counted out how many people died at each address. And so if we zoom in here a little bit, you can see that there's these little bars that he's drawn here. And so, for example, at this address, I think that's like 2 bars, or I guess 3 bars technically. So 3 people died at that address. This one, there's 4 bars. So 4 people died at this address, and so on. So you can kind of count and see how many people kind of passed away due to cholera at each address. And then he also listed out something kind of interesting, which is these water pumps. So there's different water pumps throughout the city. That's where people get their water. And so there's a pump up here, and then there's a pump here. This is called the Broad Street pump. There's a pump down here as well. There's a pump out here on the right, and then one over here on the left. So those are some of the things that he drew. And so based on just those things, I guess, and what we're seeing here, like, what do you guys notice? Anything interesting? Like, what do you see any interesting patterns with these bars? Anything that stands out to you, or just seems like kind of strange? So the pump on Broad Street is messed up. So yeah, the bar is centralized on Broad Street pump. They seem to be concentrated around there. Broad Street, high bars near Broad Street. Death around that pump, yep. There's some deaths far away from the pump, so that's also interesting, right? So if you come out here to this extremities, like this address has like a lot of that's like, it's like really hard to count. There's so many there. And then a few out here as well, right? So it's kind of interesting. These ones are actually really interesting because there's a bunch around the Broad Street pump, but then there's also a pump right here too, which is like nothing's really happening here. But then all of a sudden you have like all these ones here with a bunch of deaths. So actually what happened for these people was that it was actually like really difficult to get to this pump for some reason, like because of the way the roads are constructed. So most people here actually ended up going to the Broad Street pump. So like that's kind of interesting. So there's some kind of exceptions. And then what's also interesting is generally around the Broad Street pump, you're seeing a lot of these bars, but then notice this building here, there's no bars. So this is a brewery and there were no deaths here. And so the reason for that was because they had their own well. So they had their own kind of independent well to get water that was different from the one that was used here. So it's kind of interesting. And so they ended up being okay. But basically what you can kind of see is it seems like people around the Broad Street pump are the ones that are more likely to die. Maybe there's some contamination in the water there. And that would explain maybe why this is happening at just people who live there. This is just a zoomed in view, so you can kind of see it in a little bit more detail. Moral of the story: get your own pump. Yeah, that's pretty fair. Yeah, so that it's important to keep in mind that this is an observational study here, right? Like he didn't go in and he didn't tell these people like, okay, I'm going to pick some of you to go live by the Broad Street pump and some of you to go live somewhere else, right? Like people chose where they live to some extent, right? And so it's an observational study. It's just data as it was. There was no kind of interference in that. And so we can't really conclude causation necessarily yet in this case. But it is still interesting to see that it's like so strongly associated here. The link seems to be very strong, right? And so one thing he did do is, based on this data, he suggested to the local government to basically like take the handle off of that pump so that you couldn't use it anymore effectively. And it turned out that once they did that, then the deaths started to go down. So it's not totally clear if that was really what caused the deaths to go down, because that was also kind of like around the time that cholera was just going down in general throughout the whole country, but still kind of interesting. And so he's become famous for a lot of reasons, but they actually made a pub in his name. If you see it here on the map, so this is like a modern day map of the Soho area, and it's like basically right on Broad Street. Now it's called Broadwick Street, but basically the same thing. And it's kind of cool. In front of the pub, they had the pump here. They took it away now, but it was there for a really long time. And this was like the original one. And then if you notice here on the right, there's usually a handle here that you can kind of like turn. That handle is gone because they took off the handle. So kind of interesting. But yeah, they kind of did that to just like commemorate him. But yeah, so that's more of an example of basically sort of association. It's an observational study. We couldn't really conclude causation there. But what he did to conclude potentially causation was he went and looked at a much larger data set of companies that provide water. So this is kind of the wider entire London region. And basically what he did was, this shows you kind of the areas that are serviced by each company. So you have SNV, which is kind of doing most of this region here in green. And then Lambeth is another company that serves kind of this orange region. And so then there's also an overlap. So there's parts of London where like people are served kind of by both companies. And so what was interesting was SNV was getting its water downstream from kind of the sewage system, and then Lambeth was getting it upstream, which seems like really silly today. But anyways, that's what they're doing. And so you would think that probably SNV might have like worse outcomes. And what's interesting is, even though this is sort of like an observational study, the key thing is that people didn't necessarily like there's no systematic differences between people who live in these areas versus these areas. Like it's kind of the same set of people, same sort of income, like access to health, like access to food, access to resources. There's no like systematic differences between the people in those two regions. The only difference is the company that provides them water. That's it. There's like no other difference. And so from that perspective, if you have a situation like that where you have two data sets that are like pretty much the same, two sets of individuals that are pretty much the same, other than like one single thing, then that's almost like doing a kind of like randomized experiment in some sense. You're almost like randomly assigning some people to SNV and then randomly assigning some people to Lambeth. And so the point is, if you have two sets of people who are almost identical, except for one thing, then if you notice any difference between them, it's probably because of that one thing, because besides that thing, they're like pretty much the same. And so that's what he kind of hypothesized, was that, well, if we can show a difference between the groups of people who live in these regions, that could probably show that, there was actually something wrong with the way that they set up the company to be like downstream from the sewage system and everything. And so we can take a look at the actual results here. Yeah, so I guess treatment group is basically, you can think of it like, in this case, the treatment group is like SNV, and then control group is the one that doesn't get the treatment. So that's kind of Lambeth, if you want. So it kind of depends on how you want to, do that. And so basically he concluded that there's no difference whatsoever in the houses or people receiving supply of the two water companies. in any of the physical conditions with which they're surrounded. So effectively, he's just saying what I just said, which is that these two sets of people, there's no main difference, in terms of like the conditions where they live, in terms of the bad smells that they experience, or anything like that. It's really just they just get different water. That's it. No other systematic differences there. And so what he did was he went out, he collected data on how many houses there were in kind of each area, how many deaths there were, and then also deaths for 10,000 houses. So kind of based on what you're seeing here, any thoughts on, what you could maybe conclude from this? Feel free to share in the chat. Okay. Yeah, so basically people aren't really liking SNV here. Why is that? What are the numbers that are telling you that SNV shouldn't has an issue? The death rates, the number of deaths. So the number of deaths is definitely a lot more, right? You have 1,000 versus 98, but you also have to look at deaths per 1,000 because this is also just more houses here. So we would kind of expect to see more deaths anyway if they were kind of having the same sort of outcomes on average. So you do have to look at the death rate. So it's this third column that kind of really gives it away. And so SNV has nearly 10 times as many deaths per person effectively, or per 10,000 houses, compared to Lambeth. So that's pretty stark difference. And so, in this case, like it seems like SNV probably could be changing the way that they give their water. The fact that they're downstream from the sewage system is potentially an issue. Cool. So basically, when you're trying to assess causality, the main key is that your treatment and control need to be similar apart from the treatment. So the treatment should really be the only like fundamental difference between the both of them. And so if that is the case, then any differences in the outcomes between the two groups can be attributed to that one thing that's different between them. Does that make sense? Really good question here. Isn't it not random though? Because they did congregate in these areas for another purpose. Like maybe there was a particular reason why people lived in like one region or another, due to environmental or like cultural reason. Yeah, so he kind of ruled that out because like environmentally they looked like pretty much the same. There was no like really major difference in those regions. And then culturally too, like there wasn't necessarily like certain groups of cultures or anywhere. So it was pretty homogenous, I would say, like in both regions. But yeah, that's a good question to ask though, right? If you see something like this, like, yes, it seems like it was random, but maybe it's not completely random. Maybe people from a certain like group or certain dietary habits, related to culture lived in one area versus another, right? So like those are really good questions to ask. In this case, those were kind of like controlled for, I guess you could say, but that is a valid, very valid question though. So both were observational studies. The second one was interesting because it was a little bit, it's still an observational study at the end of the day. Like you do need to do a randomization if you really want to prove causality, but it does satisfy these conditions at least, that they were similar apart from treatment, at least as far as he could tell, right? Like he could be wrong. Maybe there was some other reasons why people moved in certain areas that is not being accounted for, right? So he might have done the best he could have in the circumstances, but maybe it's not a perfect study still. And so what happens when you don't account for this and you have like two groups of people that are different for more than just the treatment, then you have something called confounding. And the issue with confounding is basically like if the treatment and control groups have differences other than the treatment, then those other differences could be the ones that are causing the difference in the outcome, right? It's not necessarily just the treatment itself. It could be something more like underlying or some other factor. And this is especially common in observational studies. Because in observational studies, you're not deciding who gets the treatment. They're usually like self-selecting in some way. Either they selected it intentionally, or even if it wasn't intentional, maybe they were intending to do something else that resulted in them getting the treatment versus someone else, kind of like what Adam was suggesting with like, maybe they wanted to move there for some other reasons. It wasn't because they knew it was SMV, there's just some other reason, but it happened to be that those reasons were quite different in the both groups. So that's basically the issue. And so those other reasons are called confounding factors. And so an example of this could be kind of related to heart health, but think about like Gatorade or just any sports drink, right? So you might see in the data that people who have more sports drinks throughout their lifetime have a healthier heart. And so you might think like, well, that maybe, why doesn't that imply that drinking sports drinks is good for you? Well, if you look at it deeper, there's people who drink sports drinks are typically more active, right? They're more physically active. And so they happen to be more physically active. And so if you look at these two groups of people, like people who drink sports drinks and people who do not, that's not the only difference between them. There's fundamental differences in their behavior that led them to that. And so, if you're more active, more physically active, we kind of know that that's going to result in a healthier heart. And so that's kind of there's a confounding factor there, basically. And so like the underlying reason isn't the Gatorade or the sports drink, it's actually that they're working out more. They just happen to drink more sports drinks as a byproduct of that. And so that's the main thing to keep in mind is like, when you're trying to prove causation, you have these two sets of individuals typically, and you just want to make sure that they're like basically the same, other than this one thing that you're looking at. So you don't want to get confused with like too many things being different. So any questions about that? Oh, that's a good question. How can we prove the direction of the causation? So A causes B or B causes A. So the best way to do this, and I'll explain this in a second, but it's basically to randomize. So ideally what you'd want to do, like if you go back to the sports drink example, what you'd want to do is take two sets of people that were kind of chosen randomly, and we'll explain that more throughout the course, what that means. And then you'd want to assign some people and like force them basically to say like, you guys have to drink sports drinks for the next 2 years or something. And then the other group of people, you say, you guys do not drink sports drinks for the next 2 years. So you have to kind of assign it to them. And that way, that because you're assigning it, that's the thing that's going to cause the outcome. And so you wouldn't be able to like say the other way around. Like you can be pretty clear then that A causes B because I assigned A. So you have to kind of be assigning the treatment to confirm that the treatment is like causing the difference in the outcome. So direction cannot be determined by observational study. Yeah, that's true. So in general, you can't really conclude causation with observational studies. You need to have an experiment to do this. Cool. So there's some fun examples of confounding that I thought I would show you, and they're also just examples in general of like correlation does not equal causation. So this is a chart over time from 2000 to 2009. And it's showing divorce rates in Maine. So in the state of Maine, divorce rates in red, and then per capita consumption of margarine in black. And so, we talked about earlier, move together, right? Like these seem to be moving together pretty closely, like almost to a T. And it's interesting, but I mean, you have to think about, what's difference between like two different groups. In this case, the different groups are almost like years, because we're saying these have a correlation like over time. And so, 2001 versus 2000, the difference in those years wasn't just the fact that like, look, so for example, let's say you're trying to say that the per capita consumption of margarine has an effect on the outcome, which is divorce rates in Maine, right? So let's suppose this is your treatment, margarine, and then outcome is divorce rate. So the difference between 2000 and 2001, it's not just the consumption of margarine went down, like other things happened between those 2 years. Like there was a stock market crash, like all kinds of things happened. So, there's lots of effects of various things. So it's hard to say that it's just margarine. There's like lots of other differences in those two groups of 2000 people in like 2000 versus people in 2001. Right? So it's kind of analogous in that sense. There's another fun example here. So we have per capita consumption of cheese over time, and then the number of people who died by becoming tangled in their bed sheets. So that's also surprisingly associated or linked like decently strongly. I like this explanation. So more prosperity equals more butter, which means less margarine, which is less divorce. Interesting. It's a good one. So yeah, so this is another one. And then there's another kind of funny one, which is just like so crazy, but the number of people who drowned by falling into a pool, and then the films that Nicolas Cage appeared in. So yeah, I don't know about this one, but it's pretty interesting. Interestingly enough, this is the lowest. This is correlation number here, which don't worry about what correlation means right now. It's just kind of like a way to measure like how tightly linked, how closely they move together. It's 66% for this one. The other ones are like over 90%. So this is like slightly weaker of a association, but still interesting nonetheless, especially visually. It's like really close. Oh, that's such a good explanation. Nicolas Cage inspires people to be more adventurous, and then so they jump into the pool. Yeah, that is maybe cool. So yeah, so that's how that's how you can just see that there's lots of cases where things move together, but not necessarily one causing another. There could be lots of other factors at play. How do you determine if it's a random correlation versus the treatment actually affecting the outcome? So the single best way to determine that is to randomize. And so, what you need to do is basically you take your individuals and then you kind of split them up into two groups. So usually what you do is you start with like a single group of individuals, split them up into two groups, and then go to one group and say, okay, you guys are treatment, one group, and you say you're the control. And so because you split them up sort of randomly, that's the key. So you didn't split them up by like, okay, I'm going to take everybody like above 18 over here and everybody under 18 over here. Like that's really bad. You need to completely randomly split them up so that both groups like end up looking almost identical, like pretty much the same kind of. That's the key. And so that way, the only difference between them is going to be the treatment. And then you go and assign the treatment to one group, go and assign the control to one group. So one question for you guys, if I do this process of like splitting it up into two groups randomly, and I go to the first group and I tell them, you guys are the treatment. I go to the other group and tell them you're the control. Do you guys think there's any issues with that? Yeah, nice. Placebo, right? So there's one small minor detail. It's like you almost had it, but you didn't quite have it. And it's because you told them. You typically don't want to tell people which group they're in because that might bias how they feel, right? So you want to be really careful about how you do this. And so typically these are called like blind experiments, or sometimes even double blind, where the experimenter doesn't even know. Like, I don't even know what I'm giving you. I'm just giving you something. I'm giving you something. It might be the same, might be different. So that's really important too, because if you want to make sure that they're exactly like pretty much the same sets of individuals, you want to also make sure psychologically also they understand that they're the same sets of individuals. You don't want them to think that like, oh, I know I'm the treatment or I'm in the control, because then that might change their behavior. So that's also really important. Yeah, and so basically, this randomization allows you to mathematically account for variability. And so you're basically kind of taking away all factors that would have led to them choosing the treatment. You're choosing for them. And this entire process is called a randomized control experiment. So this is kind of the gold standard, the holy grail. This is how you can prove causation, is with a randomized control experiment. Because you're for sure saying there's no difference between these groups other than the treatment that we gave them. Any questions about that? Oh man, is there a way to calculate how random something is? Um, there's some tests you can do, which again, way beyond the scope of this class. But if you take more statistics, you'll do some tests on whether like a data set is potentially randomly generated or not. There's actually some tests you can do, but it's a tricky problem. When we randomize, does that prevent confounding? Yeah, exactly. You're preventing confounding by randomizing. Yep, that's like the point of it. Yep. Nice. Any other questions? Is correlation the same as association? Correlation is actually a way that we measure association. So correlation is kind of like a mathematical representation of association. It's like put a number on the association between these two things. That number is typically correlation. So we'll talk more about it later in the course, like how do you actually calculate that number? When should you use it? When should you not use it? It's actually a very specific kind of association that's being measured actually. So we'll talk about that more. Cool. So I want to show you guys a real example of a randomized control experiment. Hopefully this will be somewhat familiar. So this is a chart showing two different groups that were randomly assigned a treatment and a control. So the treatment was the Pfizer vaccine, and the control was people who did not get the Pfizer vaccine. So I mean, probably what happened was they got a needle, but there's like nothing in it. So just got a shot for no reason. But basically they kind of agreed to the study. They agreed to basically be randomly assigned, and they were aware that like you may or may not get the shot. And then they were kind of just observed over time afterwards. And so we saw kind of the incidence of COVID between these two groups. And so as you can see, some people do get it still if you get the Pfizer vaccine, but it's just way less than people who do not get the vaccine. And so this is a randomized control experiment. There were no differences between both of these groups of people, other than the fact that one group of people actually got the shot, one people did not. All the behavior was exactly the same, everything like that. Is that measurement a percentage? Oh, sorry, you're talking about correlation. I'll go back to that in a second. Yeah, so this is a real world example of randomized control experiment. In general, it's hard to do randomized control experiments because they're not always ethical. There's situations where, let's say you wanted to see like the effect of smoking on like lung cancer, right? Like you can't go to a bunch of people and be like, okay, you guys smoke for 50 years, you guys don't smoke. Like that's just not going to happen, right? So there's limits to what you can do with randomized control experiments, but if you can do them, it is the best way to prove causation. That's the main takeaway. Cool. And to go back to the question about is that measurement a percentage? So we'll go a little bit more into detail of how correlation is calculated. Actually, it's probably going to be towards the end of the semester, like the last 1/3 of the class. But it is not exactly a percentage. But we'll go more into details of that later. Any other questions? Cool. So one other last thing to keep in mind is the dictionary has its own definition of random. In probability theory, random means something very specific. So random is not the same thing as like haphazard. Random is a very, almost like not systematic, but just like a kind of repeatable way of how you're separating these groups. Like you're being very careful in the way you're doing it. You're not just being like, all right, let's just throw stuff around. Like you're being very systematic sort of in the way that you randomize. And so we'll go into more details on like the right way to randomize. But it's kind of like randomization is like in probability theory, it's like sort of understandable, sort of predictable to some extent. You can put numbers around like what are the chances of things happening. It's not just like, let's just toss out the table and like mess up the whole board game. It's a little bit more, I don't know, professional than that, I guess you should say. Cool. So since we have a little bit of time at the end, I thought it'd be good to show some responses from past semesters where people just gave advice for the course. So just kind of things you should keep in mind for the rest of the semester. So I figured might as well show you these since we have some time here. So we'll just kind of scroll these down and just kind of briefly read them. I can try to zoom in a little bit. But yeah, so stay up to date with lectures. That's a good one. Make sure you understand every part of the homework. So as you're kind of like doing the homework, make sure you're kind of getting the concepts. If you're not getting the concepts as you're doing the homework, make sure you take some time to review them. The staff is here to help, so please don't be afraid to ask or if it's office hours. I think this is really good advice. Even if you're someone who's like a little bit more shy or not as like outgoing, that's fine. Like make an effort to come to office hours and just get the help you need, because there's so many resources available, and just take advantage of it. It's all there. It's all provided for you. So you should use it. Start projects in advance. So as they're mentioning here, it's not really going to take you the full 2 weeks to do it. We usually give you 2 to 3 weeks to do these projects, but the projects are really just like a longer homework assignment. So it's not like this massive thing. But with that said, still start them in advance because they do take some time, and it's good to just, get going earlier. Another one on attending lectures. Have a Python reference sheet open for every assignment. So you'll learn more about that in the labs, but that's really good to have handy. We don't expect you to memorize like everything that you're learning in all the code. It's okay to have that reference, and for especially like really common things. So this is a little bit out to date. We don't have Piazza anymore. We have Ed. But basically, it's a really good idea to try to answer other people's questions on Ed. I kind of mentioned this last time too. Like that's going to really reinforce your knowledge and understanding of the material. So try to go through Ed, even if you don't have any questions yourself, like just try to go through and answer people's questions. You're going to help other people out, and you're also going to just understand the material better yourself as you're kind of trying to put it in words and explain it to someone else. So that's a really good practice too. Read the textbook. That's also really good. So the textbook is kind of the ultimate source of truth. So definitely check out the textbook. Read through that, keep up to date on the textbook material as we're going through the lectures as well. Super, super important. Yeah, a lot more of the same stuff. Go to office hours, Python reference sheet, office hours, Piazza, Ed. Go to lecture. Yeah. Yes, and this one's really good here. So you can rewatch the lectures, that's fine, but the chat that we have here during lecture can have some really nice discussions. I already see you guys talking right now in the chat about correlation versus causation. Like those are really good discussions to have, and be able to clarify in real time, right? That's just so valuable. You kind of have that extra help with you. You're kind of watching lecture together and like interacting. I think that's really cool. And I want to make sure we keep doing that once we go back in person too. So like, even if whether you're in the lecture hall attending in person, or you're just at home because you don't want to come in, you can still kind of interact live and still be a part of that discussion. All right, so we're going to make sure that you can keep doing that. Cool. So that's kind of the main things. Last thing I'll leave you with is just this comic from XKCD. Hope you enjoy that. Hopefully it drives in what we talked about today with the differences between association and causation. Cool. All right. Well, I think we'll start the lecture there. Thanks, everybody. I will stay on for any other questions. Just hang out. Thanks, everyone. See ya.